Good evening, everybody. Today we are going to discuss about step response of an RC circuit. Okay. So before we discuss about step response of an RC circuit, let us go for capacitor circuit. Okay. Coming to capacitor circuit. Okay. Capacitor circuit. Here, what is mean by capacitor? Okay. Yeah. Here, capacitor means when two conducting plates are capacitor means when two conducting plates are separated by an insulating medium. It's called capacitor, right? Okay, so any two conducting surfaces separated by an insulating material is called a capacitor. Okay, the charge holding property of a body is called capacitance or capacity. Okay, capacity of capacitor. Okay, here two conducting plates separated by an insulating medium or dielectric medium. It is also called as dielectric medium. Okay, then it's called capacitor. Okay, the conducting surfaces are called the plates of the capacitor. Okay, these two are conducting plates. These are connecting plates. Okay, these connecting surfaces are called plates of the capacitor, and insulating material which is present between these two plates is called dielectric. So this is also called as dielectric. Okay. Capacitor and its behavior. Okay, so you know, right? A capacitor consists of two pieces, two pieces of metal separated from each other by a good insulator. Okay, when two conducting plates are separated by an insulating medium, okay, I think of capacitor. Okay. The most commonly used diodes are air, mica, wax paper, ceramic, etc. This could be this dielectric medium could be air, mica, wax paper, ceramics, etc. Okay, so here Vs is the applied voltage across capacitor. Okay, so here physically when two conducting plates, okay, two conducting plates are separated by an insulating medium. Insulating medium is present between these two separated plates. These two plates. Okay, insulating medium is present between these two plates. Okay, here two conducting plates are separated by an insulating medium, nothing but capacitor. Okay, when voltage is applied across this capacitor, okay, this plate will get positive charge, whereas this plate will get negatively charged. Okay, let D is the distance between two plates. A is equal to area of each plate. Then we have the formula. Okay, so a voltage source is connected across the capacitor to transport charge from one plate to another plate until capacitor charge build up is equal to the applied voltage. Okay, so here Vs is the voltage which is applied across capacitor. Okay, here charge will be transported, okay, until voltage across capacitor reaches its applied voltage. Okay, okay, the voltage across the capacitor depends on how much charge was deposited on the plates and also how much capacitance the capacitor has. Okay, voltage across the capacitor is depending upon the charge deposited on the plates as well as capacitance of the capacitor. Okay, so we have the formula P is equal to Q by V. Okay, Q is, or otherwise Q is equal to CV. So where V is the applied voltage, here V is the voltage across the capacitor. Q is the charge which is deposited on the plates of the capacitor, and C is the capacitance of the capacitor. Okay, so C is equal to Q by V, where Q is equal to magnitude of charge stored on each plate. V is the applied voltage. Okay, so now how how does how does a capacitor how does a capacitor store charge? How does a capacitor store charge? Store charge. Okay, so let me have take it like this. Here, two conducting plates. This is plate A, and this is plate B. Two conducting plates are separated by an insulating medium. Okay, this insulating medium could be air or mica or any other dielectric medium. Okay, so these two are connecting plates. Okay, let me use switch over here. Let V is the voltage which is applied across this. Okay, if the switch is open like this, then okay, these two plates are neutral. Plate A and plate B are neutral. Neutral means it is having positive charge as well as negative charge. Positive charge and negative charge like this. Okay, this plate is neutral. Okay, again this plate is also neutral. Okay, two plates are neutral plates. Okay, positive charge as well as negative charge. Okay, without applying any voltage. Okay, the capacitor plates are neutral. Okay, there is no charge on the plates. Okay, now let me close the switch. Okay, let me close the switch now. Okay, after closing the switch, what will happen? Okay, let me close switch. Let me close the switch. Okay, here let VH is the voltage applied across this. Okay, so here as it is having positive charge as well as negative charge like this, positive negative like right. Okay, these two are neutral plates. Okay, without applying any voltage, these two are neutral plates. The moment you apply voltage, okay, this is positive terminal, whereas this is negative terminal, right? Okay, these electrons will get attracted by this positive terminal. Okay, these electrons will get attracted by this positive terminal. So that electrons start moving in this direction. Okay, electrons are moving in this direction. Okay, these electrons are moving in this direction means plate A is becoming more positive charge because plate A is losing electrons. Plate A is losing electrons. Plate A is losing electrons means plate A is becoming positively charged one. Okay, and these electrons detached from plate A and start accumulating on plate B Okay, because here this is positive terminal whereas this is negative terminal. Okay, these electrons are attracted by this positive terminal, so that they start flowing. Okay, away from this plate. Okay, so that these electrons are detached from plate A, and start accumulating on plate B. Start accumulating on plate B like this. Okay, so plate A getting charged with positive charge. Okay, plate B becomes negative charge one. Okay, the process of detaching electrons from plate A, the process of detaching electrons from plate A, and accumulating on plate B, is called charging of the capacitor. Okay, the process of detaching electrons from plate A and accumulating on plate B. This process is called charging of the capacitor. Okay, so here plate A attains more positive charge, plate B attains more negative charge. Plate B attains more negative charge. Okay, so here see, slowly for example, let me apply 10 volts across this capacitor. Let me apply 10 volts across this capacitor. Okay, so here slowly electrons which are present on this plate, okay, moving away from this plate as they are attracted by this positive terminal. As they are attracted by this positive terminal, they move away from this plate. Okay, so plate A becomes more positive charged one, whereas plate B becomes more negative charged one, right? Okay, so slowly the voltage across capacitor, slowly the voltage across capacitor will be increasing. Okay, let it is 1 volt. Initially, it is 1 volt, 2 volt, 3 volt, 5 volt, 6 volt, 7, 8, 9, 9.9. Okay, even if it is 9.9, also current will be flowing. Current will be flowing. The moment it reaches 10 volts, the moment voltage across capacitor reaches 10 volts, means which is equal to applied voltage. Okay, the moment it reaches 10 volts, okay, which is nothing but what applied voltage, the current flow ceases. The current flow ceases because voltage across capacitor is 10 volts. Voltage at this point with respect to this point is 10 volts. Again, voltage at this point with respect to this point is also 10 volts. Okay, so when there is no potential difference between 2 points, then no current flows. Okay, so the voltage across capacitor reaches its applied voltage, then capacitor acts as open circuit. Capacitor acts as open circuit. Okay. The point to be noted here is the current which is flowing through the capacitor is not conduction current. Okay, so just you take one resistor or inductor, you take one resistor, you apply some voltage across this resistor, then the current which is flowing through this is conduction current. Okay, because continuously, I mean, there is conduction. Okay, throughout the circuit, uh, there will be this resistor is in contact, okay, with this voltage. Okay, so the current which is flowing through this is conduction current. Okay, whereas in case of capacitance, these two plates, okay, no conducting path is present between these two plates. No conducting path. No conducting path is present between these two plates. Okay. Interior of this capacitor. Interior of this capacitor. Uh, in this. Okay. Through the interior of this capacitor, no current flows because no conducting medium is present between these two plates. Okay, if there is conducting medium between these two plates, then conduction current will be flowing. As there is no conducting path provided between these two plates. Okay, the material which is present between these two plates is dielectric medium, which is not conducting medium, which is insulating medium. Okay, this will not allow current to flow, right? So no current flows through the interior of the capacitor. No current flows through the interior of the capacitor. Okay, if current flows through the interior of the capacitor, then we can say that current is called conduction current, but no current is flowing through the interior of the capacitor as dielectric medium is present between two plates. Okay, so the current which is flowing through this, instead of saying conduction current, you can say displacement current. You can say displacement current. It is displacement current. It is displacement current. Okay. When you apply voltage across this capacitor, okay, this plate attains more positive charge, whereas this plate attains more negative charge. Okay, so you can say capacitor got charged with applied voltage. Let V is applied voltage. Capacitor got charged with applied voltage. Means some current is flowing. Current is flowing to this. This is some kind of hypothesis. Okay, current is flowing, but no current is flowing through the interior of the capacitor. Okay, you can say the current which is flowing through the capacitor is displacement current, which is equal to conduction current, okay, that magnitude is equal to magnitude of the conduction current. Okay, the current which is flowing to the capacitor is not conduction current. Okay, the current which is flowing to the capacitor is displacement current, which is equal to conduction current. Okay. Okay, you have the formula, right? C is equal to epsilon A by D. Okay, epsilon A by D is equal to epsilon. Here you have relative permittivity, and this is permittivity of for free space. Okay, okay, area of the capacitor plates. Okay, distance between two plates. Okay, so the value of capacitance can be expressed in terms of physical parameters of capacitor as it is given, right? Yeah, the voltage across a capacitor cannot change instantaneously. Okay, this is one of the properties of the capacitor. Okay, when DC voltage is applied across the capacitor, okay, when capacitor is subjected to DC voltage, that voltage, I mean, the voltage across capacitor cannot change instantaneously. Means here the voltage current relationship of the capacitor is given as I is equal to C D V by D, right? Okay. So let DC voltage is applied across the capacitor. Okay. Let you take okay, otherwise let DC voltage is applied across the capacitor. Let DC voltage is applied across the capacitor, right? Okay. So here, you know, this instant is T is equal to 0. This instant is T is equal to 0 minus instant, whereas this instant is equal to T is equal to 0 plus, just after the change of voltage. Just after the change of voltage. Just before the, this instant is just before the change of voltage. Okay. At this instant, voltage jumps from 0 to V. If magnitude of this is V, okay, voltage jumps from 0 to V. Okay, right? Now, let me make one statement here like this. The voltage across a capacitor cannot change instantaneously. Okay, means if voltage changes, okay, if voltage changes instantaneously, means within zero time you have to get change in voltage. You have to get change in voltage within zero time. Within zero time, you have to get change in voltage. Means from T is equal to 0 minus to T is equal to 0 plus. Okay, this duration is called zero time. Almost it is zero time. Okay, due to the application of sudden voltage, okay, almost it is zero voltage. Uh, then here see, you have to get change in voltage within zero time. Okay, within zero time means this part becomes zero. Okay, within zero time you have to get change in voltage, then current becomes infinity. Okay, so have to pass infinite amount of current to the capacitor, then only voltage across the capacitor can change instantaneously. Means can change instantaneously means V of 0 minus is not equal to V of 0 plus. V of 0 minus is not equal to V of 0 plus if we pass infinite amount of current through the capacitor. So, which is practically this is not possible. Practically this is not possible because we cannot pass infinite amount of current to the capacitor. It is impossible, right? We always pass finite amount of current, right? Okay, so this is impossible. This passing infinite amount of current is impossible. Okay, if passing infinite amount of current is impossible means V of 0 minus is not equal to V of 0 plus is false. Okay, so that's why voltage across a capacitor cannot change instantaneously. That is, within zero time, voltage across capacitor cannot change. Means V of 0 minus is equal to V of 0 plus. Within zero time, voltage cannot change. Voltage cannot change means whatever the voltage is available at t is equal to 0 minus, same voltage will be available at t is equal to 0 plus. Okay, so voltage cannot change instantaneously within zero time. Okay, so here what is V of 0 minus? You say it is Vc of 0 minus, Vc of 0 plus, as it is voltage across capacitor, right? Okay, Vc of 0 minus means just right before the change of voltage, just right before the change of voltage. It is the voltage across the capacitor, just right before the change of voltage. It is the voltage across the capacitor, just right after the change of voltage. Okay, so Vc of 0 minus is equal to Vc of 0 plus. In case of inductor, current to the inductor cannot change instantaneously. Okay, similarly, in case of capacitor, the voltage across a capacitor cannot change instantaneously. Okay, to bring about such a change means here, if to if voltage across capacitor change instantaneously means I have to pass infinite amount of current through the capacitor, which is impossible. That's why voltage across capacitor cannot change instantaneously. Next, one more thing is, let me make one more statement. The capacitor acts as an open circuit when voltage across the capacitor doesn't change. You know, right? I is equal to C dV by dt. C dV by dt. Okay. If applied voltage doesn't change with respect to time, means DC voltage, means when capacitor is subjected to DC voltage, what will happen? What will happen? Okay, here voltage is not changing with respect to time; it is constant throughout the time, right? Okay, if it is not changing with respect to time, means change in voltage with respect to time would be zero. Would be zero. Okay, dV by dt would be zero. That will be zero because voltage is not changing with respect to time. Okay, slope of this is with respect to time is zero. Slope of this voltage with respect to time is zero, right? So dV by dt is zero. Then current becomes zero. Current becomes zero means then current is becoming zero means capacitor acts as open circuit. Capacitor acts as open circuit. So when capacitor is subjected to DC voltage, it will act as open circuit. It will act as open circuit at steady state. At steady state only. Okay, at steady state. At transient state, it will not act as open circuit. At steady state, it will act as open circuit. At steady state, we will consider steady state response. Okay, steady state response. Okay, so under steady state DC voltage, capacitor acts as open circuit. Okay, so we should careful with these two statements. We should be careful with these two statements. Okay, the statement one is the voltage across capacitor cannot change instantaneously. Vc of 0 minus is equal to Vc of 0 plus. Okay, statement two is the capacitor acts as open circuit when voltage across capacitor doesn't change. Okay, that is under steady state DC voltage, capacitor acts as open circuit. Coming to the representation of ideal capacitor. Okay, so this is the representation of ideal capacitor. Okay, simply two lines. Okay, two plates. These are two plates, like connecting leads. Okay, here insulating medium is present between these two plates, right? Okay. The resistance of that insulating medium is infinity. In ideal case, it is infinity. Okay. You take resistance of dielectric medium. You take RT. Okay. It is infinity in ideal case. Infinity, then only no current flows. Okay. And next here, yeah. And one more thing is plates. Plates are having zero resistance. In ideal case, plates are having zero resistance. Okay. So an ideal capacitor doesn't exist, as all drugs have some leakage current. Because see, RD is not equal to infinity in practice. In practice, it is more. In practice, it is more, but not equal to infinity, right? Okay, so there will be some leakage current flowing through the interior of the capacitor. Very small. That leakage current is very small. Okay, the current which is flowing through this dielectric medium is called leakage current. Okay, as dielectric medium resistance is very high. Okay, this leakage resistance is uh, leakage resistance. You can say leakage resistance. Leakage resistance, and the current which is flowing through that leakage resistance is leakage current. Okay, that leakage current is very small. Leakage current is very small, as leakage resistance is very high. Leakage resistance is very high. Okay. So in practice, leakage current is very small and leakage resistance is very high. Okay. In practice, practically, two plates are having, okay, normally two conducting plates separated by an insulating medium, right? Okay, so this insulating medium is having very high resistance in practical. Okay, practically this is having very high resistance. Okay, leakage current is very small, very high resistance, and these plates are having some resistance. These plates are having small resistance. These plates are having small resistance, right? Small resistance in practice. Okay, so we have to represent the resistance of plates as well as resistance of the dielectric medium. So practically this will be the representation of capacitor. Okay, so the leakage resistance can be represented by connecting resistance across capacitor. Okay, this is leakage resistance of dielectric medium, which is very high in mega ohm. In mega ohms, the resistance of the plates can be represented a resistor which is connected in series to the capacitor. Okay, this is very small, almost equal to 0. So this is the representation of the practical capacitor. Okay, whereas this is the representation of ideal capacitor. Ideal capacitor. What are the properties of ideal capacitor? The dielectric resistance of the capacitor is infinity. Okay, resistance of the dielectric material is infinity, and resistance of the capacitors. Sorry, resistance of the capacitor plate is zero. Okay, practically the resistance of the dielectric material is not infinity, it is very high. If it is very high means there will be small leakage current flowing to the capacitor plate. Okay, flowing to the capacitor, right? Okay, and capacitor plates are having small resistance. Okay, so this is the representation of practical capacitor. Okay, this RH is what? Resistance of the capacitor plates. RP is what? Resistance of the dielectric medium. Okay, so here this indicates power loss. Power loss in capacitor plates. Okay, the leakage resistance can be visualized as a resistance connected in parallel with the capacitor, and the power loss in capacitor plates can be realized with a resistance connected in series with the capacitor. Okay, next. Coming to step response of an RC circuit. Okay. Here we are going to switch. Okay, series RC circuit. R is connected in series. R is connected in series with C, right? Okay, so let I of T is the current flowing to this after closing the switch. So meaning of this is at T is equal to 0, you are closing switch. Okay. For T less than 0, for T less than 0, what will be the circuit? Which was in open condition. Which was in open condition. Okay. This will be the circuit, right? Because for T less than 0, switch was in open condition, right? Okay. Here, this instant is T is equal to 0. This is for T less than 0. This is for T greater than 0. Here closing the switch at T is equal to 0. Here closing the switch at T is equal to 0. Means the switch has been opened for a long time, right? Okay. Then for T less than 0, this will be the circuit. This will be the circuit means what will be the voltage across capacitor? Okay, voltage across capacitor is 0. Means V of 0 minus is 0. V of 0 minus is equal to 0. Okay. So, right, voltage across the capacitor cannot change instantaneously. Means V of 0 minus is equal to V of 0 plus is equal to V of 0 is equal to 0. Here we placed uncharged capacitor. Here we are placing uncharged capacitor. Okay, so initial voltage across capacitor is 0. Initial voltage across capacitor is 0. Okay, within 0 time, this instant is 0 minus, this instant is 0 plus instant, T is equal to 0 plus instant. Within 0 time, voltage cannot change. Voltage across the capacitor cannot change instantaneously. Okay, whatever the current is available at T is equal to 0 minus, same current will be available at T is equal to 0 plus. That's why V of 0 minus is equal to Vc of 0 plus, which is equal to 0. Which is equal to 0, right? Okay. So initial condition is V of 0, which is equal to 0. Okay. You can also have the circuit like this. Okay. Instead of connecting switch R C, you can Vs U of T. Okay. Okay. This circuit is same as this circuit. Here closing switch at T is equal to 0, right? Okay. If for T less than 0, switch is open. This was in open condition. Okay. So here instead of connecting switch like that, you can also have circuit like this. VSU of T means for T less than 0, Vs is 0. Vs is 0. For T greater than 0, voltage is equal to Vs. Applied voltage is equal to Vs. Because U of T is unit step function. Okay. It is equal to 0. U of T is equal to 0 for T less than 0. U of T is equal to 1 for T greater than 0. Already we have discussed about this, right? Okay. So let me apply KVL around this loop. The KVL equation around the loop can be written as Vs is equal to R I of T Vc of T. Okay. Vs is equal to Rc. Here I of T is equal to C dVc by dt, right? C dVc of T by dt plus Vc of T. This is what after applying KVL around that loop, we're going to have this differential equation. Vs is equal to Rc dVc of T by dt plus Vc of T. Means this is first order. This is first order non-homogeneous differential equation. It is first order non-homogeneous differential equation. Okay, so the solution of first order non-homogeneous differential equation is composed of two solutions, two parts. It is composed of two parts. Okay, so the solution of the above first order non-homogeneous differential equation is given by Vc of t is equal to natural response plus steady state response, or transient response plus steady state response. Okay, it is composed of two parts. Okay, so as it is, as the previous equation is first order non-homogeneous differential equation, as you are going to find the response. Here the response is voltage across capacitor. Okay, voltage across capacitor is composed of two parts. Okay, the solution of above non-homogeneous first order differential equation is composed of two parts. Complete solution is equal to complementary, mathematically complete solution is equal to complementary function plus particular integral, right? Okay, particular integral, right? Integral. Okay, so complete response is equal to transient response plus steady state response. Transient response plus steady state response. Okay, this is also called as natural response. This is also called as natural response. This is also called as forced response. Okay, so complete solution of first order non-homogeneous differential equation is composed of two parts, namely complementary function plus particular integral. Okay, so complete response is equal to transient response plus steady state response, right? Okay, so Vc of t is equal to natural response Vcn of t plus Vc of t, forced response. Okay, natural. Okay, so Vc of t is equal to a1. Complementary function can be written like this, right? Some constant into e power alpha t. Okay, this steady state response, okay, which is equal to some only constant only. Sorry, it is only constant. Okay, steady state response is only constant because the input which is applied across RL circuit is constant. Okay, this is the input which is applied across RL circuit. Okay, DC voltage, right, which is constant throughout the time. Okay, so this force response is always the type of the input which is applied across RL circuit. So the input voltage is always constant. If the input voltage is constant, means force response would be constant only. Would be constant. So Vc of t is equal to a1 e power alpha t plus k. Okay, let us find alpha. Okay, a1 and a are computed using initial and boundary condition. Okay, so let us find alpha. Okay, alpha can be obtained from the characteristic equation. Okay, you know, right, what is the characteristic equation? Okay, from the characteristic equation, you know, right, this alpha can be determined. We know, right, Vs is equal to RC dVc by dt plus Vc of t, right? Okay, so in order to find alpha, this is non-homogeneous equation. In order to find alpha, you consider homogeneous equation. So let me consider homogeneous equation. RC, instead of writing d by dt, you write alpha plus 1 into Vc is equal to 0. Okay, so RC alpha plus 1 is equal to 0. Then alpha is equal to minus 1 by R. So Vc of t is equal to a1 e power minus t by RC. Put alpha in the above equation, then you will get Vc of t is equal to a1 e power minus t by RC plus k. Okay, let us find the value of A. Okay. So there are two ways of finding the value of A. Okay, first way of finding the value of A is anyhow VC of infinity is equal to A, right? Okay, so put this in that equation, that is Vs is equal to RC dVc of t by dt plus Vc of t. Okay, Vs is equal to RC d Vcf by dt plus Vcf. Okay, so which is equal to RC dA by dt plus A. Okay, this will be 0. Okay, differentiation of constant is equal to 0, right? Okay, finally you'll get A is equal to VA. Okay, this is one way of solving. One way of getting the value of A. Another way of getting the value of A is as it is series RC circuit. Here VAC is the voltage which is applied across this, right? Okay. Earlier we made one statement, right? Okay. What is that statement? Under steady state DC current, capacitor acts as short circuit. Under steady state DC current, capacitor acts as short circuit. Under steady state DC current means when time approaches infinity. Okay, when time approaches infinity, capacitor acts as open circuit. Sorry, capacitor acts as open circuit. Okay, whereas inductor acts as short circuit. Okay, when time approaches infinity, under steady state DC current, inductor acts as short circuit. Under steady state DC voltage, capacitor acts as open circuit. Means when time approaches infinity, capacitor acts as open circuit. Okay, so when time approaches infinity, capacitor is acting as open circuit. Means these two terminals are kept open like this. Okay, replaced by open circuit like this. Okay, then the voltage between these two terminals is VC of infinity. VC of infinity means voltage across capacitor when time approaches infinity. Okay, here this is what Vs. Okay, so when this is acting as open circuit, when capacitor is acting as open circuit, then no current flows through the capacitor. Then whatever the voltage is there between these 2 points, same voltage will be available between these 2 points. Means VC of infinity is equal to Vs only. VC of infinity is equal to Vs. Okay, so directly you can have VC of infinity, which is equal to forced response, steady state response, VCF, which is equal to Vs. This is another way of getting the value of A. A is equal to Vs using initial condition. Okay, this is boundary condition. Okay, boundary condition. Okay, using the initial condition, that is at t is equal to 0. T is equal to 0. Vc of 0 is equal to, already we have the equation, right? V of t, Vc of t is equal to a1 e power minus t by rc plus a, right? Plus a, right? Okay, this is the complete solution, right? For non-homogeneous differential equation, right? Okay, so in this equation, you use initial condition. Okay, using initial condition in this equation, then Vc of 0 is equal to a1 e power 0 e power minus 0 by rc plus a. We put, already we got the value of a is equal to vs. Okay, then a1 is equal to minus vs. The final expression for capacitor voltage is Vc of t is equal to, after after including all values, value of a is vs, the value of a1 is minus vs. Okay, then which is equal to a1 is what? Minus vs. Okay, e power minus t by rc. Okay, plus a is what? Vs. Here, which is equal to Vs into e power, sorry, Vc of t is equal to Vs into 1 minus e power minus t by r for t greater than 0. For t greater than 0. One can also write like this: Vc of t is equal to Vs into 1 minus e power minus t by rc into u of t. Into u of t. Vs into 1 minus e power minus t by RT into u of t. Instead of writing t greater than 0, one can also write Vc of t is equal to Vs into 1 minus e power minus t by RT into u of t. Yeah, voltage across resistance. VR Vc Vs VR Vc Vs. So VR of t is equal to Vs minus Vc of t, which is equal to, okay, can solve this. What is the yeah, Vs minus, what is Vc? Vs into 1 minus e power minus t by RT. Okay, this is exponentially increasing. Here the voltage is increasing exponentially. Here the voltage is decreasing exponentially. Sorry, decreasing exponentially. Coming to charging current to the capacitor. Current to the capacitor. Current to the capacitor is VR by R. With, as these two are connected to this, simply VR by R is current to the capacitor. Current to the capacitor as well as resistor. So Vs by R into e power minus t by R. Okay, so we get graphs like this. Okay, so complete response is actually it will be like this. Complete constant. This is transient response. Okay, from this instant to until it reaches final value, the response is called transient response. The response due to the sudden application of voltage is called transient response. Okay, the response after transient has died out is called steady state response. Steady state response. Okay, steady state response. The steady state will occur when time approaches infinity. When time approaches infinity. When time approaches infinity, steady state occurs. Okay, under steady state DC voltage, capacitor acts as open circuit. Capacitor acts as open circuit. Okay, capacitor will act as open circuit. Open circuit when time approaches infinity. Under steady state, it acts as open circuit. The open circuit like this. Okay, so as it is acting as open circuit, voltage across capacitor is directly equal to applied voltage. Okay, so it is composed of two parts: transient response and steady state response. Next, coming to this I of t. Okay, exponentially decreasing, right? Exponentially decreasing. Okay, initially the value is Vs by R. Okay, exponentially decreasing. Finally, it becomes 0 when time approaches. Okay, this is another way of solving. Yeah, step response of a circuit is its behavior when the excitation is the step function, which may be a voltage or a current source. Okay, so here an RC circuit with voltage step input. V of 0 minus is equal to V of 0 plus, because voltage or capacitor cannot change. Here actually, if we use uncharged capacitor, this will be 0. If you use charged capacitor, then there will be some voltage across capacitor. You take V0. Okay, if some voltage is present in capacitor, you take V0. Okay, after solving the differential equation, finally you'll get for t less than 0, it is V0. Okay, for t greater than 0, you're going to have the expression like this. You're going to have the expression like this. Okay, so here see, general equation can be written like this. You know, right? Vc of t is equal to a1 e power minus t by tau. Here tau is RC. Tau is time constant RC plus a, right? Let me use initial condition Vc of 0, which is equal to anyhow, you know, A1 is minus Vs, minus Vs plus so here see this will be K. So which is equal to one thing, this is Vc of 0, Vc of 0 this is minus Vs, okay, e power minus t by tau, sorry, is equal to this is what Vs, Vs e power 0 is 1, okay, plus Vc of infinity, Vc of infinity, okay. So here let this is V naught, V naught, okay. See if it is having 0 initial condition means that will be 0, okay. Here let it has some initial value V naught, okay. V naught, you know, this is final value Vc of infinity, okay. This do one thing, what will be A1, okay. Sorry, actually we have to get A1, A1 and A, actually we have to get A1 and A, okay. You know already, you know, Vc of infinity, right? So you put as it is A1 e power minus t by tau plus, let it have some initial value, it is not 0, v of 0 is not equal to 0, okay. So here this will be Vc of infinity, right? Then what will be A1? A1 is equal to v of 0 minus Vc of infinity, Vc of infinity, okay. This part becomes 1, okay. So v of 0 means t is equal to 0 means A1 e power minus 0, okay. This part becomes 1, so A1 plus Vc of infinity, so A1 is equal to v of 0 minus Vc of infinity, Vc of 0 minus Vc of infinity, okay. So finally you can have uh, general formula like this: Vc of t is equal to Vc of t is equal to, okay, Vc of 0 minus Vc of infinity into e power minus t by tau plus Vc of infinity, plus Vc of infinity, okay. So this is the general formula, okay, where Vc of 0 is V naught, okay. Vs plus V naught minus Vs e power minus t by tau. Here Vc of infinity is what? Vs. Vc of infinity is Vs. Okay. Initially the voltage across capacitor is V naught. Okay. So starting value of voltage across capacitor is given. Okay, exponential increasing. So what will be the general formula? Okay, general formula is equal to, let me write it here. General formula V of t, which of t is equal to Vc of infinity plus Vc of 0 minus Vc of infinity into e power minus t by tau, where tau is equal to RC. Tau is time constant. RC is equal to RC. Okay. So let me define time constant here. Okay. So when okay, finally we have expression like this. With zero initial condition, Vc of t is equal to Vs into 1 minus e power minus t by RT with zero initial condition. Initially, the capacitor is uncharged. Initially, there is no charge in the capacitor. Okay, initial value is 0. So we got the final expression like this. Okay, so if t is equal to tau, if t is equal to tau, v of t is equal to v of tau. You can say v of tau is equal to Vs into 1 minus e power minus RC by RC, RC by RC. Then which is equal to 0.632 into Vs. Into Vs. Okay, so if you draw tangent, okay, then it intersects final value when time t is equal to tau. Okay, the response will be 0.632 Vs. Means it is a time, we can define time constant like this. It is a time taken by the response. Here the response is voltage across the capacitor. It is a time taken by the response to reach 63.2% of its final value. 63.2% of its final value. Final value is yes. Okay. Okay. So let me solve problem. Let me solve this problem. The switch in the given circuit was in position A for a long time. Position for a long time at t is equal to 0. Okay, the switch moves to B. Determine the voltage across capacitor. Okay, here capacitor at t is equal to 1 second, t is equal to 4 seconds. Okay, let us find the expression for voltage across capacitor, right? Okay, so either you use this expression Vc of t is equal to A1 e power minus t by tau minus t by tau plus a plus a, which is equal to A1 e power minus t by tau plus Vc of infinity. A is steady state value. Okay, A is the voltage across capacitor when time approaches infinity, right? Okay. You can also use general expression. Okay, Vc of t, okay, is equal to, what is the general expression? Vc of infinity plus V of 0 minus Vc of infinity Vc of 0. This is also Vc of infinity. Into e power minus t by tau. T by tau. Right? Okay. Either you use this expression or this expression. You will get the same value. Right? You can use any one of these two expressions. Okay. But we have to find initial value as well as final value. Okay. Initial value means Vc of 0. Okay, here Vc of 0 minus is equal to Vc of 0 plus, because voltage across capacitor cannot change instantaneously. Okay, so here this instant is T is equal to 0. Okay, here the switch will be in position B at T is equal to 0. Which is moved to position B at T is equal to 0. Then for T greater than 0, which will be in position B only. Okay. The switch was in position A for T less than 0. For T less than 0. Okay. So here you have to find initial value. Initial value means, okay, Vc of 0 plus voltage across capacitor T is equal to 0 plus. Okay. This voltage at this instant is Vc of 0 minus. Okay, voltage at T is equal to 0 minus is Vc of 0 minus. Voltage at T is equal to 0 plus is Vc of 0 plus. Okay, voltage across capacitor cannot change instantaneously. Means whatever the voltage available at T is equal to 0 minus, same voltage will be available at T is equal to 0 plus. Means Vc of 0 minus voltage doesn't change instantaneously. Vc of 0 minus is equal to Vc of 0 plus which is equal to Vc of 0. So we have to find initial value first. Okay, initial value means voltage across capacitor T is equal to 0 minus. Voltage across capacitor T is equal to 0 minus, because voltage across capacitor T is equal to 0 minus equal to voltage across capacitor T is equal to 0 plus, which is equal to Vc of 0. So we have to find Vc of T at T is equal to 0 minus. Okay. So T is equal to 0 minus, what will be the circuit? Okay. T is equal to 0 minus, this will be the circuit. Okay. T is equal to 0 minus, and one more point here is, this is for T less than 0, right? This is for T greater than 0, right? Okay. This instant is T is equal to 0. This instant is T is equal to 0 minus. This instant is T is equal to 0 plus. This instant is T is equal to infinity when time approaches infinity. Okay. For T greater than 0, steady state occurs at T is equal to infinity. When time approaches infinity, steady state occurs. Okay. For T less than 0, steady state occurs at T is equal to 0 minus. Steady state occurs at T is equal to 0 minus, because this is the final value. For T less than 0, this is the final value. Okay, final value occurs at T is equal to 0 minus for T less than 0. Because for this portion, okay, you're going to have the final value at this instant. For this portion, you're going to have the final value when time approaches infinity at this instant. Okay, so steady state occurs at T is equal to 0 minus. Under steady state DC current, capacitor acts as open circuit. Okay, so at T is equal to 0 minus, the circuit would be like this. T is equal to T is equal to 0 minus voltage source 24 volts V kilo ohm 5 kilo ohms a T is equal to 0 minus steady state occurs under steady state DC voltage capacitor acts as open circuit, then voltage across capacitor VC of 0 minus, then VC of 0 minus is equal to, you can use voltage division rule. Voltage across 5 kilo ohm resistor is nothing but VC of 0 minus. Okay, you can use voltage division rule, then you'll get VC of 0 minus is equal to 15 volts. Written right, for T less than 0, the switch is in position A, the capacitor acts as open circuit to DC. Yeah, VC of 0 is equal to VC of 0 minus equal to VC of 0 plus is equal to 15 volts. Okay, now we have to find VC of infinity. VC of infinity. Okay, VC of infinity means the circuit will be like this. At T is equal to infinity. At T is equal to infinity, the circuit will be like this. When time approaches infinity, capacitor acts as open circuit. Capacitor acts as open circuit. So voltage across this is VC of infinity. For T greater than 0, steady state occurs at T is equal to infinity, right? So voltage across capacitor at T is equal to infinity equal to VC of infinity, which is equal to applied voltage 30 volts. So VC of infinity is equal to 30 volts. T is equal to, okay. So for T greater than 0, you have to find time constant. For T greater than 0, you have to find time constant. So for T greater than 0, the circuit will be like this. Simple article. Okay, is 0.5 millifarad. Okay, this is 4 kilo ohm. So simply tau is equal to RTH into C. Okay, RTH into C. Only here we have only one resistance. Okay, if you have two resistances, like this, two resistance across capacitor like this, what will be the time constant? Okay, between the terminals of the capacitor, you have to find RTH. Between the terminals of the capacitor, you have to find RTH. Okay, into C gives time constant. Okay, finally, after putting all values, okay, you'll get the expression like this. This is the expression for T greater than 0. Okay, so T is equal to 1, V of 1 is equal to, so this much one. So T is equal to 4 seconds. V of 4 is equal to 27.9 volts. The voltage is given like this: 30 U of T volts. 30 U of T means 30 into 1 for T greater than 0. Because what is U of T? U of T is unit step function. Unit step function. Okay, this is equal to the value of this is equal to 1. Okay, so for T less than 0, U of T is equal to 0. Okay, for T less than 0, U of T is equal to 0. Means voltage will be 0 for T less than 0. Voltage will be 30 for T greater than 0. For T greater than 0 is equal to 30. Okay, so you have to find initial value. Right. So T is equal to 0. T is equal to 0, which is open. It is open. T is equal to 0. Which is open at T is equal to 0 means it has been closed for a long time. Okay, before opening the switch, right? Okay, here also switch will be open. Okay, here this instant is t is equal to 0 minus. Okay, you have to find initial value. Okay, Vc of 0 minus is equal to Vc of 0 plus is equal to Vc of 0. You have to find initial value. So t is equal to 0 minus, what will be the circuit? T is equal to 0 minus steady state occurs, because for t less than 0, final value occurs at this instant. Okay, so steady state occurs. Okay, and the steady state DC voltage, capacitor acts as open circuit. So the circuit will be, one more point is, for t less than 0, this voltage will be 0. 30 into 0. Already we have discussed about it, right? Okay, so 30 into 0. 0 volts. 0 volts means short circuit. 30 less than 0. It is equal 0 minus also, it is 0. Right? So 10 ohm. Capacitor acts as open circuit. So this will be Vc of 0 minus voltage, which was in closed position. We are opening switch at t is equal 0. T is equal 0 minus, which is in closed position. Okay, so Vc of 0 minus is what? Vc of 0 minus initial value is equal to 10 volts. Okay, let us find time constant. Tau for t greater than 0. For t greater than 0, what will be the circuit? The circuit will be like this. For t greater than 0, 30 into 1, 30 volts. Okay, 10 ohms. Okay, 20 ohms capacitance. This is the circuit for t greater than 0. Okay, so here tau is equal to what? Tau is equal to RTH into C. Okay, RTH is the resistance between the terminals of capacitor, right? So what will be RTH? In order to find RTH, you have to make all sources 0. So 30 volt source is replaced by short circuit. Then this is 10. This is 20. Between the terminals of the resistor, you have to, between the terminals of the capacitor, you have to find RTH. Okay, the resistance between the terminals of this capacitor is what? 10 into 20 by 10 plus 20. Okay. Initial value is, already we have discussed about it. Okay, initial value is 10 volts. Okay, then the current which is flowing through that is flowing through this 10 ohms for t less than 0 is minus v by 10, which is equal to minus 1 amp. Okay, so after finding RTH, you have to find Vc of infinity. Vc of infinity means, okay, at t is equal to infinity, capacitor acts as open circuit. So circuit becomes 10 ohms, 20 ohms. Capacitor acts as open circuit. Vc of infinity, this is 30 volts. This is circuit at t is equal to infinity. Capacitor acts as open circuit. Okay, voltage was 20 volts. By using voltage division rule, you can find Vc of infinity 20 volts. All values you can find. Okay, you have to find the value of I. going to find the value of I. I means the conventional strength. Okay, we got the value of voltage across capacitor. Okay, you apply KCL at this node, you will get this equation. After getting this equation, you can find I. Sorry, you can find I also. Okay, so V is equal to 10 volts for t less than 0, because at t is equal to 0 minus voltage 10 volts. For t greater than 0, this is the voltage. For t less than 0, minus 1 amp. For t greater than 0, it is okay, you can also use this. Use this.
Sir, unmute your microphone.